the next 2 weeks. So yesterday we sort of summarised our plan, we had a look at the exam, give us an awareness of the sort of work that we're going to do, and then when we get to the end of this, and we start doing some more exam revision, hopefully we start to see, yeah, I can do this, sort of building up a fair bit of confidence that we know how to do this stuff. So today we're going to go through the introductory concepts, okay, so that's chapter 1 of the textbook. I'm going to summarise some of the skills that we did there, and then we're going to look at Differential Calculus chapter 2. So make sure you're bringing this booklet along. It's a synthesis of all of the notes books. It doesn't have all of the details, but it includes the essence of what we need to know. Alright, so first one, chapter 1a is about exponential functions. And the comment that I've got there is exponential functions, the basic one, a to the power of some variable where a can be any number. Remember, e is a number. So e is the exponential function with Euler's number, and they are asymptotic to the x-axis. So they look like this. That's the basic one. Of course, we can shift them around and so forth, but that's where they are default. They have that asymptote at y is 0. Now we're going to contrast those very quickly with 1c, where we have logarithmic functions. And logarithmic functions, so for instance, the function ln of x will exist provided x is greater than 0. And so what does that mean for the graph of it? That if you graph the basic log function, ln, or log, doesn't matter, we'll talk about that in a moment, but they are asymptotic to the y-axis, that they exist for values of x that are positive. Alright, and of course again we can shove that around and so forth. But just there are the basic shapes for it, for the exponential and the logarithmic function, and they are the inverse of one another, right? If you flip that about the line y equals x, they're symmetrical about it. Okay, so that's 1a and 1c. Let's look at 1b and we'll go through some of these skills. We've got solve and simplify. So the first one is log 10 root 10. Okay, so we need to make sure we show all of the steps here to get the answer. Alright, so we know this is a logarithm in base 10, and we know that because there's no subscript written here. There's no subscript written here, which means the default base for a logarithm is 10. And so we need to express this as a single power of 10. So what we have is 10 times 10 to the half. Alright, 10 by itself is 10 to the 1, isn't it? You can put it there, you don't have to. Now that those two have the same base, we can add the powers together. And 1 plus a half is going to be 3 on 2, or 1.5. And now that we've expressed it as a single power of 10, it simplifies to 3 on 2. Okay, so log of 10 root 10 is 3 on 2. Alright, the next one we have is ln of 1 on top of e. So ln is the natural logarithm. It's a logarithm with a base of e. So another way that this could be written, right, is log in base e of 1 on e. Remember, that's the base, right? Although this is the correct notation that we use. So what we want to do is we want to express this as a single power of e. Because it's at the bottom, we can take it to the top and write the power as a negative. We've expressed it as a single power of e, so now it evaluates to the power. Okay, we've got 3 ln2, take ln4. We want to write that as a single logarithm. We want to bring them together. So before we can do that, all right, we know ln a take ln b will be ln of a on b. But we need to move this power out the way first. So we get rid of that coefficient. So we can write this like that, right? ln2 to the power of 3. We can do the inverse of the 2. And 2 to the power of 3, that means 2 times 2 times 2. That's going to be ln of 8. All right. Now we can collect them as a single logarithm. And simplifies to ln2. Very good. D, we have an exponential equation to solve. We have 3 to the power of x take 2 equals 9. So the first way we can try and solve this is by equating the bases. All right, we can make the bases the same, and we can equate the powers. So 9 we can actually express as a power of 2, right? 9 can be written as 3 squared, and because the bases are the same, therefore the powers are the same. So therefore x take 2 equals 2, and we would have x is 4. All right, so that's one way we can solve this, by equating the powers, equating the bases and then equating the powers. The other way, we're going to solve this same equation, but we're going to do it using logarithms. Okay? And we'll use the natural logarithm. So if this is the statement we have, the first thing we're going to do is perform the natural logarithm of both sides. It doesn't matter whether we do log in base 10 or natural logarithm, it doesn't really matter. You can do either. So we're going to have 3 ln of 3 to the x take 2 is equal to ln of 9. Now, this power can come out the front, right? So that's going to be x take 2 multiplied by ln of 3 is equal to ln of 9. Right, ln of 3 is just a number, so we'll divide both sides by ln 3. It's very important for me to let you guys know, right? ln of 9 on ln of 3 is not equal to ln of 9 on 3. Well, it will in this circumstance, but let's change it, because that wouldn't work actually in this circumstance, but it's not a general rule. All right, ln of A on ln of B is not equal to ln of A on B. That's not a rule that we should use. So we're going to keep it like that. And then we solve for x. We've got x by itself. All right, so we can evaluate that to get this same answer here. Okay, so that's logarithms. We talked about 1c. Let's jump down to trigonometric functions. Stop me if you have any questions. All right, and hopefully I'm going slow enough as well. I'm going to speed through it. Okay. Trigonometric functions. We have sine of 3x equals half. We want to find the values of x that make this true. All right. So what we're doing is we're looking at our unit circle, and you'll find the unit circle overleaf. I've printed it there for you. And we're saying when is the y values, remember sine is the y values, when is the y value equal to a half? And so we're going to get this location and this location. The angle is pi on 6 and 5 pi on 6. Now, with this question, we're not restricted to a domain, right? We're not asked to solve just the first revolution. We don't have a domain here. So I've done that on purpose. If we did have a domain, because of this 3, we would have to multiply the interval by 3, right? And consider 3 rotations. All right? We don't have a domain. So that means we need to answer all possible solutions. What are all of the solutions to it? Because there's infinitely many, right? It goes on in both directions. So what we're going to have here then is we'll have 3x is pi on 6 and 5 pi on 6 plus or minus k2 pi for k e z. Alright, what does that part mean? It means adding or subtracting any integer, that's what this part means, any integer, for k is some whole number. So any integer multiple of 2 pi. Okay? So in year 11 we focused specifically on this part, and at the very start of the year we did talk about this a little bit. Okay, so that's going to be all of the solutions. So then to get x by itself, we divide both sides by 3, right? And so when we divide this side by 3, we're going to get pi on 18 and 5 pi on 18 plus or minus k2 pi on 3, and then that statement there, 4k is an integer. All right, so here, you know, we're getting marks there for the solution, but we get the extra mark to show all of the solutions to that trigonometric equation. All right, part B, find tan of 5 pi on 6. Tan of 5 pi on 6. Well, tan is sine divided by cos, right? So what we're doing is we're finding sine of 5 pi on 6 on top of cos of 5 pi on 6. Now, we can look at our unit circle to determine these values. We should remember from here, sine of 5 pi on 6 is half. We just got that one up there. So we've got half at the top, and at the bottom, cos is going to be root 3 on 2, but it's negative because it's on the negative side. And then we just do AD on BC. So we're going to have here minus 2 on top of 2 root 3, which is minus 1 on root 3. Now, of course, we expect the answer to be negative. Let's justify why. Remember on our unit circle, remember our all silly turtles crawl. So in this quadrant, all of the ratios are positive, sine, cos, and tan. In this one, just sine is positive, which means tan, what we found, is going to be negative. All right, move on to the next one. Find the equation of the graph. So this is the default sine function, right? A sine b of x takes c plus d. And we've done these sort of transformations ad infinitum, right? We started them with the roller coaster, we're reflecting on it. We've even been doing them with the wine glasses. Okay, so A is the amplitude, that's stretching it away from the x-axis. B is the period. B in a trig function tells you how many wavelengths in 2 pi. That's stretching and compressing it in the horizontal direction. C is horizontal translation, so you're picking it up and moving it to the right or to the left. And then D is vertical translations, that's moving it up or down. So if this is the basic function and we're presented with this graph, we want to determine the values of A, Tom, B, C, and D. So amplitude is the distance from the principal axis to a peak or a trough. So our principal axis is at 1 and it goes all the way up to positive 4, so that distance there is 3. We have an amplitude of 3. And what we see is we've got 2 wavelengths in 2 pi. So that means the value of B is going to be 2. 2 because 2 wavelengths. There's no horizontal translation. And then the vertical translation is the principal axis, positive 1. That's how much it's been lifted up from the x-axis. Very good. So that's the summary of chapter 1. Let's get into chapter 2 then. So chapter 2 is what we had our first test on, and chapter 2 is solely differential calculus and the rules of differential calculus. So we're going to go through all of these questions together. In 2A, first principles. So here's the formula for first principles. And the function that we're doing it for is x squared plus 2x. So let's get started. F dash of x is equal to So let's explain that. All right, f of x plus h, that's this entire component. F of x plus h. Take away f of x. Very important that we have brackets there so that that negative will distribute. All right, and all these first principles problems are the same. It's very methodical. It's a beautiful process to follow. We're going to expand. We're going to collect the like terms, cancel h, and apply our limit, and voila, there's our answer. So let's go ahead and do that. Remember to write the limit. Okay, that's correct notation. Here's our expansion. Okay, we've expanded. X squared will cancel, and 2x will cancel. And everything left should have a h in it. Everything left should have a h in it. So that's one way of sort of checking along the way if you've made the correct expansion and collection. So let's factorise, cancel the h. And remember, we're writing the limit right up until the step where we apply the limit, which is basically a substitution for 0, and that's going to be our answer. That is, what is it? F dash of x. That's what we've followed through. F dash of x is this one here. And we know that's the answer. We know that's the answer. Why? Because of the exercise we're doing next. Simple differentiation. If you differentiate this, 2x plus 2, 2x plus 2, we've confirmed our result. So let's move on to simple differentiation then. So we've got y equals 3x plus 2x squared on top of x squared. We're going to differentiate this. Now, for simple differentiation, we need to express everything at the top of the fraction as a power of x. Alright, so straight away, like we could use the quotient rule here, but it'd be a long way to do it. Alright, so what we should be doing is, what's the simplest way here? I'm going to split the denominator, and then I'm going to simplify it. Okay, so now we're ready to differentiate. We're very clear. Here's y, here's y, here's y. Differentiate. dy or dx. Alright, you need to be very clear. You can't just go equals, equals, equals. That doesn't make any sense. This is the same function, and now we're differentiating. And how could that be written? Minus 3 on x squared. Okay, chain rule. We've got y equals x squared, take 3x, power of 5. Alright, so this is where we have a function to the power of n, and so we can go straight to the derivative. It's going to be n f of x to the n take 1, and then multiplied by the derivative of the inside here. N f of x, n take 1, times f dash of x. And you know, it doesn't matter what order you write these terms in, order of multiplication doesn't matter. That 5 you could distribute into this one, doesn't matter, that's fine as is. Differentiate without simplifying, you would have seen that on the front page of the exam yesterday. Alright, so that's chain rule. Now for the product rule and the quotient rule, I've written the rules there, but we'll come back to them so that we can do them with a trig and with an exponential and with a log. So I'll write some problems up there in a moment for the product and the chain rule. Let's jump down to derivatives of exponentials. So we have y equals 2e to the power of 3x plus 4. Alright, so this is e to the f of x. So if you're looking at your notes here, the derivative is going to be f dash of x, e to the f of x. So we can straight away jump to the derivative. The 2 is going to hang out because it's a multiple. Alright, whenever it's a product, it's just going to stay there. And then the derivative of 3x plus 4 will be 3. And then we have e to the 3x plus 4. Alright, and that would simplify 6e to the 3x plus 4. Alright, logarithms. So we've got y equals ln 2x to the power of 3 take away 4. So we look at logarithms, ln of f of x, the derivative is going to be f dash of x on top of f of x. So the derivative here would be 6x squared on top of the function, 2x to the 3 take away 4. And we have cos of 2x. And so we've got cos of some function is going to be minus f dash of x of sine of the function. So that's going to be minus 2. The derivative of 2x is 2. So minus f dash of x sine of fx. Let's be clear. Yep. F dash of x equals. Very good. All right. So let's do one with the product rule, one with the quotient rule. Alright, so for the product rule here, we've got u is e to the x, and the derivative of e to the x is e to the x. We've got v is ln of x, and the derivative of ln of x is 1 on x. And then we'll just smash those together. U dash v plus u v dash. Alright, for the quotient rule, we have u on top of v. So we're going to u is x, u dash is 1. V is cos of x squared. So that cos of f of x. And so then v dash is going to be minus f dash of x sine of f of x. And so then for the quotient rule, dy on dx is u dash v, take away u v dash, okay, x times minus 2x will be minus 2x squared, and these two negatives will make a positive in the end, they'll make a positive. And all of that is on top of v squared. So that's cos of x squared. Okay, now let's point out something that's applies here as well, is it's cos of x squared squared. That does not simplify to cos of x to the power of 4 or cos of x to the power of 4 in here. It's cos of x squared. All right, this is a function of x squared, and whatever that value x to, then we're going to square it. Okay, so that's big maths for you. All right, so that's going to be our final answer there, and that's quotient rule done. All right, so what I would like us to do today then is we've just had a very cursory glance at chapter 1, chapter 2. Okay, so we haven't done anything overly complex here. We've just sort of said these are the skills that we learnt. And so probably a good starting point might be to have another look at some of the review sets, right? Have a look at the review sets, or even pick some questions as you scroll through the textbook, just to re-familiarise yourself with the content of chapter 2. Chapter 1, that's what I'd like us to dedicate today's lesson to. All right.